Alright, this is another episode for the electronic structure methods module, and here we will be learning about some useful results which we kind of have used throughout the semester and which we will use extensively in the following screencast on density functional theory. So my idea is that we will kind of look through these notes here, and then when we come to density functional theory, some of these mathematical operations will prove far easier, or at least we will be able to focus on concepts rather than on the maths. Okay, so the very first thing is, well, first of all, my apologies for some of the untidiness in these lecture notes. They have been written in a bit of a hurry, but I hope you can read them. So the very first result is we are looking at a one-electron operator, script O, which written in its many-body form, you will have a sum over the electronic indices, and you will have n of these script OI's. Alright, now we will assume, as we often do in this course, that these operators are spin-free, so in coordinate form, O will be a function of the coordinates of the electron Ri, and R of course is a vector here. Now what we want to show is that the expectation value, when you have an n-electron wave function, this is not a Slater determinant. This is an n-electron wave function, which, if you remember, is generally expressed as a potentially infinite combination of a number of Slater determinants. So we want to show that the expectation value of this operator O in this for this n-electron wave function, so psi O psi, is equal to the density times O of R, where O of R is one of these, integrated over all space. So it's quite a simple expression really. And now before we go on, just think about what O might be. O could be the electron nuclear interactions, and in which case what we are saying here is that the expectation value of the electron nuclear interactions with this n-electron wave function is simply the density times the electron nuclear interaction operator integrated over all space. And you know this to be correct. If you think about it for a while, you know this has to be correct. Now how do we show this? Well, in the language of density functional theory, by the way, the electron nuclear interaction operator is often called the external potential. So I've written the sort of density functional kind of operator for O as Vxt, which is external potential, is equal to the sum over the external potentials for each of the electrons. And therefore we would then have the equivalent result that the expectation value of the external potential with the wave function is the density times Vxtr dr. Okay, so to prove this, we need to just remind ourselves as to how do we define the density. Now the density is defined here as rho of r is n times the integral of the psi star psi, and integrated over all electrons except the first one. Now this should have been R2, it's a mistake on my part. So we have psi is a function of R, R2, R3 all the way to Rn. And then we integrate over electrons 2 to n, skipping the first one. That's which I've chosen to be just R. Now to be completely correct, this should not be, psi is not dependent only on the electronic coordinates, it's dependent on the spin coordinates too. So we really need to have an integral over all spin coordinates, including the first one. Now if you're wondering where this came from, go back to the lecture notes on H2, where I have shown you how the density is defined in general. Alright, so to be completely correct, we would have this kind of an integral with the correction that this goes from R2, R3 all the way to Rn, and we would have an integral over all the spin coordinates too. Alright, so let's start here. Now the reason why I could skip the spin integrals is because my operators in the end are going to be spin independent, but anyhow, that's the technicality. Alright, so we want the expectation value of psi or psi. Now that's simply the integral. Now once again, I am deliberately ignoring all the spin coordinates, but to be correct they should be included here. So it's this integral over psi star, the n-electron form of the operator, so the sum from I goes from 1 to n of O r I, and then psi, integrated over all coordinates. Alright, so now we are here. Now if you think about it, it doesn't matter what Ri is in this sum. The electrons are equivalent. These are dummy indices. We're integrating over all of them. So the integral involving O of R1 is the same as the integral involving O of R2, etc., all the way to O of Rn. So I can write this simply as n times psi star O of R1 psi integrated over all electrons. And this is just a statement of the fact that all electrons are equivalent. Okay. With that, now let's separate this integral, which is now you have an integral for each electron. We pull out the integral over dr1 or r1, and then in curly parentheses we've got n times the integral of psi star r1 r2 all the way to rn mod squared, integrated over all coordinates except r is equal to 1, which is over here. Now you can see that this thing in the curly braces is the density. It's rho of r1, and that proves a result. So what we get is that the expectation value of psi or psi is the integral over r1 O, the operator of r1, times the density of r1. Now the 1 here is simply a dummy index. You can just drop it to get the result you wanted here, that this is equal to the density times the operator integrated over all space. Now this is quite a nice powerful result, because we will often find ourselves dealing with one electron operators, and in which case we can write them down like this. Now there's one caveat which I haven't mentioned here. Let's have a look at this, where this comes in. Alright, so up till this step here we are completely general. As long as O is a one electron operator, then this step holds. So this expectation value is equal to n times the integral over psi star O psi. Now in this next step here, I pulled the operator O out, and I brought the psi star and the psi together into this curly braces. Now you can only do this if O is not a differential operator. That is, if O is a multiplicative operator. So for example, let's take a counter example here. If O was the kinetic energy operator, that's the Laplacian, minus 1/2 the Laplacian for each electron, then you could not pull a Laplacian which operates only on psi. You could not pull it out of this into this place here, where it now will be operating on psi star psi. It's not possible. So however, if O is just a potential which depends on the position, there are no differentials involved, then you can do this. Alright, so this result holds only for multiplicative operators. So the electron-nuclear interaction is allowed, an electron interacting with a field is allowed, but it's not, the kinetic energies, you cannot do this. Okay, so that's the first of the results we've got. The second one is that it's a sort of corollary of the previous result. It's if psi was a single determinant given by spin orbitals chi1, chi2 all the way to chi-n, where each of the spin orbitals now is a spin function times a spatial function, then this density is written as the sum of I goes from 1 to n of phi I squared. Now you notice, we've seen this for the H2 case, where we showed this explicitly, and then what I said after that was that it hence follows that this result also applies for the n-electron case. But let's show how it's done here. So first of all, we start from the definition of the density. Once again, I am simplifying the derivation by eliminating the spin coordinates. So remember, we will have an integral. The density is given by n times the integral of psi star psi, and integrated over all electrons except the first one, and this time I've got the indices right. And we would also have an integral over all the spin coordinates, including the first one. But here we are deliberately ignoring that. Okay. Now we could start from here, or we could use the Slater-Condon rules. Now what I'd like you to do, by the way, is to start from this expression here and show that you get the density is equal to this sum over phi I squared. Here let's use the Slater-Condon rules. Right, so we know that for a one-electron operator of the form O1 is equal to the sum over I goes from 1 to n of one-electron operators Hi, we've seen this, then the Slater-Condon rules state that the expectation value of O1 with a single determinant psi on both sides is equal to the sum over the electronic over all electrons, so I goes from 1 to n of chi I h chi I, or in the short notation I h I, and we often write this as just h I I. Okay, can we use this? Well, if I want to use this, I need to write the density as an operator of the sum over some one-electron operators. Now I haven't shown this to you before, but I'm going to show it to you now. The density operator rho hat of R is defined as the sum of Dirac delta functions, where the Dirac deltas are written as delta of R minus Ri. So effectively what this is it's you've got n electrons scattered in space at positions Ri, and at each electron there's a Dirac delta, because they are point particles in this approximation, and the density operator is simply a sum of all these Dirac deltas. That is, it's a sum of all these point particles. Okay, so let's say we're given this, and let's see how it goes. So rho of R would then be the expectation value of this density operator rho hat with these single determinant wave function on both sides. Now we know from the Slater-Condon rules this is equal to the sum of the expectation values of this one electron operator with spin orbitals on both sides. So then this would be the sum I goes from 1 to n of chi I rho hat chi I. This would be in the sum I goes from 1 to n of chi I star at x prime. Now x here includes the spin and spatial coordinates. Now each of these rho hats is a Dirac delta, so it's delta of R minus R prime and chi I x prime integrated over dr prime and d sigma prime. So we're integrating over space and spin. Now I am going to skip a couple of steps. I want you to fill them in. The spin integral is trivial, isn't it? There's no spin integral. There's no spin dependence in the Dirac delta, and chi I star and chi I have the same spin functions in them. So when you integrate over spin d sigma prime, you will get a 1. That leaves you just with the integral over dr prime, and well, the Dirac delta just collapses that integral onto one point. R prime is equal to R. So we end up with just phi I of R squared summed over I goes from 1 to n. And that's the result we wanted to show. So this expression here for the density is quite general. It's valid for any single determinant wave function. Alright. Okay, so those two are done. Now I want to show you a bunch of results now, which we're going to use a lot in density functional theory, and these all relate to functional differentiation. Now, in case you wanted to revise what functional differentiation is, I suggest you look at Appendix B in Carsten Ullrich's book on time-dependent density functional theory, which you will have available online. Okay, I'm going to pause this here for a little bit. All right, back to functional differentiation. So let's have a look at the three main definitions we're going to be using. Now remember what I've already said in class before is that there is a formal mathematical way of functional differentiation, which is what we're going to go through here. But at the very end, I will also show you the informal kind of not quite rigorous, but it works physicist approach, which could be quite fast for a normal functional differentiation. All right, so the definition of the functional derivative of a functional f, which is a function of phi, with respect to phi at y, is the limit epsilon tends to 0 of 1 over epsilon. In curly braces, we have f evaluated at phi plus epsilon times Dirac delta function. Now here's where the other coordinates come in. So f is evaluated at x, but the y, this y, comes in through this Dirac delta. So basically what you're doing is you're perturbing the argument of f at, you're changing it at one point y. Alright, it's like a little blip. Now if you've read the Feynman lectures where he talks about the least action principle, it's a lovely lecture which you should look at. This Dirac delta lets you make a little blip in phi, and then you see how f changes because of this blip. Now from that modified f, we subtract the original f, and then we take the limit epsilon tends to 0, and that's our functional derivative, which is formally pretty much what you would do. In fact, it's formally identical to what you would do if you were doing a normal derivative. Now there's a product rule which looks, if you squint a little bit and convert these deltas into d's, this is the product rule for a standard derivative of the product of two functions f and g. There's also a chain rule. Now this is a bit different. If f is a functional of gamma and gamma is a functional of phi, and you're differentiating with respect to the innermost coordinate phi, then this is given by the integral dy prime of what you would recognize as the chain rule in standard differentiation theory. So the functional derivative of f with respect to gamma, the functional derivative of gamma with respect to phi. Just a point to note is that the y which appears here is also here, and then this dy prime is linked to the intermediate differentiation. Alright, so let's now just use these results and see how it works, how they work. Carsten provides more text and more kind of explanation as to what's going on, so please look there if you need any more help. So here's something we're going to do quite often. We have density, rho, remember, is given by the sum over I going from 1 to n of phi I star phi I. Phi I is the spatial part of the spin orbital chi I. Now we will frequently need to perform this kind of a derivative, delta, the functional differentiation with derivative with respect to chi I star at x. Now if you look here, we've already done the spin integration, so we've kind of got rid of the spin parts, so we have only the spatial parts of chi I, which means, well, how do we differentiate the phi I with respect to chi I? So what we're going to do is we're going to deal with something that's kind of a step, rho tilde, which is, if you look at, let's see how rho tilde is defined first. Rho tilde is now a function of x, not r. So x includes r and the spin coordinate, and it's a sum of chi I star chi I, where each of these chi i's is a function of x. So now what we've done here is we haven't yet performed the spin integral over this of this thing. So if we did perform the spin integral, if we integrated rho tilde of x with respect to sigma, then you would get rho of r. Alright, so this is just one step before getting rho of r. Now this is rho tilde of x is of the right form, because we can actually now differentiate with respect to chi I star. So let's see how it's done. Alright, so this is our job. We want to show that the functional derivative of rho tilde with respect to chi I star is equal to chi I and a delta function of x prime minus x. Now, where did the x prime and x come from? Well, rho tilde is a function of chi of x prime, and I'm differentiating with respect to chi I star, which is a function of x. Alright, so let's see how this works. Well, I need the definition of rho, so we're going to use the definition of rho from here, sorry, rho tilde, that's here. The only change I'm going to make is that first of all, it's now a function of x prime, and I'm going to make the sum go change the dummy index. Instead of an I, I'm going to call it a j. The reason for that is because we're differentiating with respect to chi I star. We do not want this index I to coincide with these dummy index in this sum. So I'm going to convert this one into a j, sum of a j. Alright, and then we need to use the definition. Remember, the definition says we need to evaluate this quantity rho tilde by including a little blip. So we need to modify the function at one point. Now let's think about what we want to do here. So let's go back to the definition, which is up here. Right? We need to find out where this function we are differentiating against, differentiating with respect to, so phi. We need to find out where phi is and add this epsilon times this delta function to phi, and then evaluate the functional with this kind of modified function in it. Now here, rho tilde is a functional of all of these chi i's. There are n of them, and if we, as we should treat the chi I and chi I star as independent functions. Now, if you've forgotten why we need to do this, well, a short answer is that these are complex functions. So there's a real part and an imaginary part, and these two pieces are completely independent of each other. So we could either differentiate with respect to the real and imaginary parts separately, or we could simply say we'll take a linear combination and we will differentiate with respect to the function and its complex conjugate separately. Now PLR explains how this is done quite nicely. I have given you all a reference to the location in PLR in the past, but I've forgotten which footnote it is in. I suggest you simply look at the index and search through and find this footnote where he describes how this is done quite clearly. Alright, so what we're going to do now, we need to differentiate rho tilde with respect to one of these. Now we've got to find that one, and that one is going to be modified with this epsilon times a delta. Okay, just one of those chi i's is going to be modified with this epsilon times a delta, and that's the important piece here. So let's get back to this seemingly complicated thing. In this first sum here, I'm going to take, so this is a sum over j. For one of those j's, j will be equal to I, and it's that case only that I want to modify that epsilon times delta. Alright, so let's do it. And I see I have made another mistake here. This should be an x prime, and this should be an x prime here, and all of these have to be x primes. The only x that appears here should be in this delta. Unfortunately, I can't make changes to the PDF, but I hope you will make changes in your notes. So remember, there's an x prime here, there's an x prime here, and here, and here. The only x on the right hand side is in this delta function. All the rest are x primes. Okay? Alright, so now let's have a look at the first part of this. So this first term in the curly braces, the first sum. When j is equal to I want to include an epsilon delta of x minus x prime. Now the way I'm going to do that is quite simply adding a Kronecker delta, multiplying the epsilon Dirac delta by a Kronecker delta of ij, which means it switches on only when j is equal to I, and that's exactly what I want. For j not equal to I, we have the original rho tilde appearing in here. There's no modification by this epsilon delta. Okay, and we have got this epsilon delta appearing only modifying the complex conjugate, and that's because we are differentiating with respect to the complex conjugate, and that we leave all the functions without the complex conjugate intact. So now we need to subtract off the original function rho tilde from the modified one, and you can see that the only term that will survive will be the epsilon delta x minus x prime times chi I. All the rest will cancel off with this term here, and that leaves us this simple result that this functional derivative is delta of x minus x prime times chi I of x prime. There should be a prime here. Of course, it doesn't matter at this stage because the Kronecker the Dirac delta will make x equal to x prime. X prime equal to x in any case. So that's the first of the results we need. Here's another which we're going to use quite often. The Coulomb energy J, which I've written here as a functional of rho tilde, is 1/2 the integral over rho tilde x1 rho tilde x2 divided by r12, not x12, it's r12, and integrated over all space and spin coordinates for x1 and x2. Now, in order to differentiate this with respect to chi I star, what I'm going to need is the chain rule. Alright, so let's use the chain rule here. A little bit of a pause while I just see what I've got ahead. Alright, so we're going to use the chain rule. Now the chain rule, let's go back to the definition of the chain rule. It says that when you have, here we are, when you have a functional which is a functional of something else, then we have this derivative written as the integral over an auxiliary coordinate y prime, and then we use a chain rule under the integral. So let's go back and do this here. So here J is a functional of rho tilde and rho tilde is a functional of the chi i's, and that's why we have this chain rule needed. Okay, so we write this then as the integral over dx prime, that's our auxiliary coordinate, x prime. It must not be the same as the coordinate in here, which is x. Then we have the functional derivative of j with respect to the rho tildes at x prime, that's where this links in, and then the functional derivative of rho tilde at x prime with respect to this thing here, which is chi I star x. Now we already know what this thing is equal to. This is going to be equal to chi I x, should be x prime, of delta x minus x prime. But what is this? What is the functional derivative of j with respect to rho tilde x prime? So let's have a look at this, just this one term now. This functional derivative, which is the functional derivative with respect to rho tilde x prime of this entire integral in the curly braces. Okay, now we've got two possibilities for rho tilde. There's one here and there's one here. Now you can see what's going to happen. This behaves almost like a square. Now if this was just x squared and you were differentiating x squared with respect to x, you would get 2x. You're going to get something like that here, but let's see how it happens. Alright, so in the first case, let us assume that we could have, by the way, in this derivation I'm going to be skipping a few steps. I do want you to fill them in by applying the definitions, the definition of the functional derivative for yourself. You do have to do this. Alright, so in the first of the cases, we could have this, the functional derivative operates on this first term here, and in the second we're going to have it in the second term here. Now what do I mean by this? Well, what I really want to do is to modify both these functions, rho tilde here and rho tilde here, with epsilon times deltas. And what we do want to do, so we'll have a rho tilde plus epsilon delta over here and a rho tilde plus epsilon delta over here. Then we need to cross multiply these terms and we will get a rho tilde times rho tilde. Then we'll have linear terms in epsilon, and then we'll have quadratic terms in epsilon. Now I don't care about the quadratic terms in epsilon, because when we divide by epsilon we will be left with an epsilon in the numerator, and when that's set to 0, that term will just drop out. We are interested only in the linear terms. And when you keep just the linear terms, you will find that you end up with two such integrals involving delta functions. And when you apply the delta functions, they will collapse one integral each to give you what I've got here. Now these two integrals are identical because x2 and x1 are dummy coordinates. We're integrating over all space and spin coordinates. So we could just as well make x2 is equal to x1 is equal to just, I call them both x1 here, and then we drop the half and we get our result, which we need is that the functional derivative of j with respect to rho tilde is rho tilde divided by r prime minus r1 integrated over all x1. Okay, putting it all together then, so the functional derivative of j with respect to chi I star is the integral over the auxiliary coordinate chi prime, x prime of this term here, which I've now brought down, times the functional derivative of rho tilde with respect to chi I star. Remember that was here, and that's simply chi I times this delta, so that's brought in here. Apply this last delta, and that collapses the x prime integral, and then we are left with the integral over rho tilde r minus r1 dx1 times chi I x. Now this term here is simply the Coulomb potential of the density rho at point r. So this is often written as, and we will often write this as simply Vj of r. So we have a multiplicative potential, the Coulomb potential of this density, which operates on orbital chi I at x. We will make use of this result quite often, so this is something which I would like you to see. You need to go through it on your own. Now if you have any, if you're not sure, for example, the crucial point here is how do we go from this line here to these two here. You need to ask me, but this is something which I think you should be able to work off by simply following the definition of a functional differentiation, functional derivative, which is this one here. You need to apply this definition rigorously, and you will get the results I have been showing. Okay, let's have a look at, I think there are two more I would like to show you, but they are quick now. That was the hard one. We will often want to differentiate the kinetic energy functional. Now the kinetic energy functional, which will be called Ts in our density functional language, where S stands for the single particle approximation. That's given simply as the sum over the kinetic energies of each of the spin orbitals in turn. Now this is something you've seen quite often when we did Hartree-Fock theory. So it's minus a half the integral of chi I with the Laplacian chi I. So our question now is, what is the derivative of Ts with respect to chi k? I've chosen the k now, just to make it different from this I. Chi k star at x. And once again, we need to apply the definition. So the definition is limit epsilon tends to 0, 1 over epsilon, sorry for the mess here, curly braces, and then we need to modify this kinetic energy only for the case I is equal to k, because we're differentiating with respect to chi k, and then we have a star, which means we only modify the chi k in the bra side of this matrix element, and we modify it using epsilon delta x minus x prime. And in order to ensure that this epsilon delta x minus x prime is added only to chi k star, I multiplied by a Kronecker delta of ik. So it will only apply to chi k star. Alright? Now that's the only, once you've got this step right, the rest kind of follows, because then you simply expand this term, subtract off the original kinetic energy with the unchanged orbitals, and you're left with just one term here. You'll have the Dirac delta kinetic energy operator, and chi k x prime integrated over x dx prime. Apply the Dirac delta, it collapses this integral, and you're left with minus a half Laplacian chi k x as expected. So here's a quick way. This is the physicist's way of kind of, if you wanted to quickly do functional differentiation, then this is what you would do. 1. Differentiate with respect to chi k star as if it was a variable. So in this particular example here, we see there's a chi k star which will appear in here on the brass side when I is equal to k. Okay, differentiate this expression with respect to chi k star, and for all the other cases I is not equal to k, you will get zeros. Only for I is equal to k will you get a non-zero value. Differentiate with respect to that. The chi k star will vanish, will give you 1. Then drop one integral. So the integral which is in this matrix element, drop it, and you're done. That's it. This is what we end up with, minus a half Laplacian chi k x. Alright, so those are the useful results. Now I will go over some of these again when we are going through the density functional notes, but I would like you to be fairly comfortable with the material here before you start to work through the mathematical derivations in the density functional notes. Alright, so this is the end of this particular set of lectures.